In this experiment, we're going to be working with inductors similar to the capacitors as we did last week. So we're going to look at the voltage and the current through the inductor. Now, the experiment is asking you for 42.7 millihenry. We do not have a 42.7 millihenry inductor, so we have to make up something which is close. So let's measure this one. And this one is giving us 38.6 millihenry. And we're going to connect the two inductors in series, and I'm going to come back to the measurements after this to show you something else. This one is 2.56 millihenry, so we're going to add them up. Now there's a internal resistance of the inductor that you're gonna find out. So here I have my L. If I just convert that thing to this R, this is 7.4 for this iron core inductor, and for the other one which we measured before, this is 56.1 ohms. So you're going to add up these two resistances to find the total resistance of this combinational inductors. Now we're going to connect the resistor in series with our two inductors. Notice that the two inductors were connected in series to make it closer to the 42.7 that we wanted, and we are looking at across the resistor. This is channel 1, which is basically it's our function generator, and we are looking across the inductor. So we're going to look at the voltages, and as before we are looking for the voltage and the current. When you connect those, you get these two waveforms, and one, if you divide by the resistance, gives you the current, the one across the resistor, and the voltage across the inductor. So they have to be out of phase, and you need to find a phase difference between, or phase shift between these two signals, which basically gives us the phase shift between the current and the voltage, which is supposed to be around 90 degrees. Okay, let's see if you can find that. Go ahead.
So first you have to change the position of the mouse. So they're aligned to the peaks of both sides. Then you have to find the delta, which is the phase shift between the two. Ours right here is 90 micro. So you take 90 times 10 to the negative 6 times 360. And then you multiply that by the voltage. By the frequency, which is 2500, about 2508 times 2508, and you get an answer of 81, which you're aiming for 90, but there could be an error using two inductors right here. Okay, so you're going to do the same concept, same frequency, except you're going to use the mouse, change your delta shift for a triangle waveform. You see triangle right there. And it's going to be 2.5K once again for this one, and then you have to do the same procedure with also 360.
No, we don't care about the phase shift for this one. Phase shift is only for the sine wave. And what you're seeing is basically you're seeing here's the voltage waveform across through the resistor, which is the same as its current waveform. And here is what you have is the voltage across the inductor, which a voltage across the inductor is V equal to L di over dt. So, which is basically the derivative of this shape that you have here representing the current through the inductor. So now you want to maybe bring them a little bit closer to each other so it looks a little bit nicer, and then you're done with this part. For the last part, you switch the waveform from the triangular waveform to the square waveform. Again, you're going to be looking at the square waveform input and its derivative, and make sure that you have that formula, which is V equal to L di over dt, when the amplitudes which you find from channel 1 and channel 2, they should match that calculations.
And
Here's what it looks like before you fine tune it.